Hey, good morning, everybody. Looks like we're going to be doing this Zoom, huh? So I appreciate you being here. We're going to work through some examples for integration by parts today. Some of these examples are going to get pretty complicated, but in terms of the exam, we're still on schedule to have the exam on Thursday. The level of difficulty in terms of problems that I would ask you for integration by parts will not be what you see here today. I'm going to keep any integration by parts problems simple, basic. And so you don't have to worry about that, like learning all of this in the next like 48 hours. But we still will have the test on Thursday. So just make sure that you're prepared in terms of having gone over. I think I sent a couple of old exams to look at, review your homework. And yeah, any questions on that? We're good.
I just logged on. Did you say that integration by parts would or would not be on the test?
It will, but they will be basic problems. They will not be complicated like the ones we're going to do today.
Okay.
If we have a question about the old test that you sent from like last semester, do we discuss that right now or at the end of the class?
That office hours or if you can't make my office hours, you can send me a text and then we can try and figure it out. I am going to hold my office hours today, but they're going to be through Zoom and they're going to be by request. So you would have to send me a text, say, hey, can you meet up in Zoom? And then I'll meet you in Zoom, or I'll just talk to you on the phone, whatever works better.
All right, some works.
Okay. I have not made the exam, so I don't know how long it's going to be, but looking at my old exams, you can kind of get a feel for the length and types of problems that I've asked in the past. But like I said in the email last week, like, don't let that be the only thing you study, right? Make sure you're looking at everything. Homework, problems I did in class. Yeah.
So with the exam, would you be like omitting any of the problems, or it's just like 100% through and through?
Yeah, you have to do all the problems. Yes. You mean like if I gave you like 12 and say do 10 of them or something like that? Is that what you're saying?
Yeah, that's what I'm talking about.
No, I'll expect you to complete all the problems on this exam. And the future exams, I might give you like, I'll take your best 8 out of these 10 or something, but not for this one. You're also allowed to have all your reference sheets, like your formulas, everything that is in Canvas under the, what you can bring to the exams under files. But you need to bring those yourself. I'm not going to provide you anything during the test. Calculator, right?
I don't know if it's already been asked, but can we use our reference sheet on the test?
What reference sheet?
The packet of all like
Yes. Yeah, all those formulas, yes.
Okay.
Was it like 6 pages?
Yes.
But that's not the only thing. There's, there's other stuff you're allowed to have as well. Although for this exam, there's really nothing else that you need other than this. But in future exams, you'll need the other stuff.
Okay, thank you.
Okay. All right. Well, if you have any other questions, we can talk at the end. So last time we were talking about integration by parts, and basically we have a formula, right? We have this formula right here, and the little ultraviolet minus voodoo, right? So this is the formula. There's a couple of different versions of this. I believe the way I wrote it in class was, we have an integral we're trying to do, right? It's some function u times the derivative of some other function that's equal to ultraviolet u times v minus the integral of v times the derivative of u. And I talked about the transferring of the derivative and how what you're trying to do is see if you can turn an integral that you don't know how to do or that's very complicated into an integral that will be easier to do, right? That's kind of the point of it. So with that said, let's do our first example. Today's examples, I'm going to be working directly from the notes. And these problems just kind of like touch on different complexities that you can find with these problems. So our first one is called a basic one. Okay, a basic, oh, let me silence my phone, hold on. I wasn't expecting to see. Oh my gosh. Okay. All right, so the first one's a basic one. We did something similar to this in class last week, but this one, there's an additional 10x in here, which kind of adds just a small layer of complexity to it. So let's solve this integral, and we're going to be using integration by parts, but I told you that's kind of the challenge as this class progresses. You know, what tells you you need to use integration by parts? Well, first thing that would tell you is that there's nothing else that we have that will work. Like, you are not allowed, because this is multiplication, you are not allowed to just take the antiderivative of those separately, right? That's not the way it works with integrals or with differentiation, right? You don't take derivatives of products by doing each one. Same thing with antiderivatives. So we're going to try and think of integration by parts now and using this table. And the table, the way that I do it is I always am going to have to establish or assign what u is going to be and what dv is going to be. And I have the freedom to choose that. And what I'm thinking about is the new integral is going to have v and du. So it's going to have the derivative of whatever I call u, the derivative of it is going to be in the new integral, and whatever I call dv, the antiderivative of it will be in the new integral. So anyone have an idea of what we should choose for u here?
X.
X. And that's because the derivative of that in the new integral would be just 1 or 1 dx. And I like that. I like the fact that it became nicer in the new integral. And then the other piece then by default has to be the sine 10x dx. That's what it has to be. So it's kind of like two pieces, right? You got the x here, that's your u, and then everything else here becomes your dv.
Would 10x be wrong because it's inside of the sign?
Would it be wrong? What do you mean?
Yeah, to use for u.
Yeah, because it's inside of the sine function, you would not want to use 10x. Now, if you were doing basic u substitution, then maybe it would make sense to do 10x,
Mhm.
but not for integration by parts.
Okay.
So just to clarify, whenever you do integration by parts, you're gonna like u and dv is gonna be the entire equation. You can't just take
Yep.
sine dv, it's like part of it or something.
That's right. You've got to account for everything you see. Everything that you see in the integrand has to be accounted for. All right. Once I get the table set up, I differentiate down and I integrate when I go up. So the derivative of u is, derivative of u, yeah, which is the derivative of x, which is just 1 dx. Make sure you include the dx there. And then this one is a little bit tricky, but we did talk about it in class last time. We tried to come up with like a generic formula for when we had, remember when we had a linear expression inside of a function. We had to like scale by doing a 1 over a out front. So refer back to your notes from last week. Who's got the antiderivative of sine of 10x for me?
Negative 110 cosine 10x.
Negative 1/10 Cosine, good, 10x. So we know the antiderivative the antiderivative of sine is negative cosine. But because there's a 10x inside, we have to scale by the 1/10 to kill off that 10 when the chain rule comes in. Questions? All right, once we've got our table set up, what we're going to do is use the formula. Okay, so that our answer is going to be equal to, first thing is ultraviolet. So that's these two multiplied, that's this times this, all right? Those two multiplied together. Now, when I do that, watch the way I write it. I'm actually going to do the negative 1/10 first. Then I'm going to put the x, then I'm going to put the cosine 10x. That's just the clean way to write things algebraically, because we normally like to put the constants out front, then if there's any x's, and then some trig function afterward. Now I put minus, and now I like to leave a space in front of that integral sign that I'm about to put here. So in case I need to pull a constant out, I'm gonna leave a space here. So the next part is to fill in this integral with the new integral, which will always be these two multiplied together. So I'm going to take the 1 dx and multiply it times that negative 1/10 cosine of 10x. So when I do that, I'll go ahead and for this first problem, I'll go in a little slower here. I'm going to put negative 1/10 cosine of 10x. And then I'm going to put times the 1 dx. And I chose to put the 1 dx on the back side instead of out front, because we've always had that dx on the far right side. So that's why I wrote it in that order. I'm going to rewrite everything. I'm not doing an antiderivative right now. I'm just going to rewrite. Now, because I have a constant inside, I'm going to pull that constant out. And so when I pull it out and it hits the negative sign, it now becomes a plus. And now I have a 1/10, and then I have my integral, and then I have cosine of 10x dx. And that integral is better, right? It's better than the original one because I no longer have the x in front of the trig function. I just have the trig function by itself. So I can use what we, again, talked about last class, and the fact that there's a 10x inside of it, the 10x is linear, I'll have to scale again. So I'm ready for my antiderivative here. Who's got my antiderivative for this right here? Anyone?
Negative sine 10x times 10.
Negative, wait, hold on. Negative, do we need a negative? We're taking the antiderivative of
No, it's
cosine.
just sine.
Just sine, right?
1/10 sine.
1/10. Okay, so we need the 1/10 to scale out that 10 that comes out if we were to do chain rule derivative on this. So the antiderivative of cosine is positive sine 10x, but we need the 1/10 to kill off that 10 if we were to take derivative. And I'm missing something.
Plus C.
Plus C. Yeah, plus C. Okay, and then put this together. Final answer here, negative 1/10 x cosine 10x plus 1/100 sine 10x plus C. There we go.
I'm sorry. Just real quick, can I
Yeah.
see the way you scale the derivative of like cosine 10x, or just so I can see how? Because I kind of forgot how you did that from last class.
Okay, do you want me to give you what we finally concluded as the general formula, or do you want me to see it derived, like how we got to that formula?
I guess just how you got to there. How you got to that point.
How we got to, okay, so then I'm gonna do it by a specific example. If we were trying to do just this integral, right? What I would do is I would do a basic U substitution. I would let U be 10x. This is basic U substitution, not integration by parts. I would take the derivative of this, which would be 10 dx. And now I'd start replacing things. So this integral now becomes cosine. Oh, you know what I need to do? I need to scale this because I'm trying to replace dx, but I have a 10 dx, so I'm off
Oh,
by 10. So I
okay.
scale 1/10 right there. And then when I rewrite the problem, it comes cosine u times 1/10 du. The 1/10 can come out. And now I just take the antiderivative cosine, which is sine. And then I replace the u with 10x.
Okay, cool.
Got it?
Thank you.
So, and that we concluded that that would work if this was any linear expression. Ax plus b, then this will always be 1/a right there.
Okay, thank you.
Okay. Yep. Any other questions?
Basically, you're just doing like U sub on that integral.
I'm sorry?
You're doing U sub on that integral part.
On this one, yes.
Yeah. Okay.
Mhm.
But does that only work if it's linear?
That's right. Only works if it's linear inside.
Okay.
Yep. And when you're doing a problem like down the road, this problem right here, cosine 10x dx, you do not want to be doing U substitution. You want to know the formula to go backwards, because if you have to do U substitution on this, that's the type of thing that's going to cause you to not be able to finish a test. Maybe not this test, but like future tests, like if you have to do U substitution for that step, you're never going to get through the other problems because you're taking too much time to do the stuff that should just be coming from your mind. So I'm just telling you, I'm just letting y'all know. Okay, next one. All right, that is what I would consider to be a basic integration by parts problem. There wasn't anything special about that. We picked our U, our dv, we did the table, we plugged things in, got a new integral, no big deal. Okay. Now here's one that I'm calling a not so obvious integration by parts. And this does tie into last class. We did do a problem like this, just not this one specifically. So when you look at this one, you go and you're like, well, is there anything I can do like basic U sub or something like that? And we can't, all right? There's nothing we can do. So we go with integration by parts, which means we have to choose a U and a dv. And we said just a minute ago that we have to account for everything that's in there. But do you all see that there's really only like, there's that and that, right? I mean, that's all we have. There's only two pieces to this integrand. So one of them has to be U and the other one has to be dv. So any ideas what you're going to let the U be?
Well, if we're taking the inverse, the derivative of the inverse sine, isn't that technically 1/the square root of 1 minus x squared?
Okay, so you're saying if we did this as our dv, I'm not sure if that's what you're saying. If we did this like this, and then go up, it would be 1/the square root?
No, isn't it the other way? The derivative
the
of
other way.
inverse
Okay,
sine?
good.
Yeah, it's the other ways. Yeah.
Okay, so we couldn't do the antiderivative of that. What we can do is if we put the sine inverse of pi x here, that I can take the derivative of because we covered that a couple of sections ago. If we do that sine inverse of pi x there, that forces us to put the dx, or if you'd like, you could put 1 dx right there. And that's your only choice. You don't really have any other choice but to do that. By the way, the dx always has to go with the dv. You can't put the dx up here because then you'd have to take the derivative of the dx, which would be a second derivative, and the integration by parts doesn't work that way. So we're going to do dx always here. And now we differentiate and we integrate, right? Now, the bad news is that the dv, when we do the antiderivative of 1, we just get x, right? Antiderivative, not derivative. Antiderivative of 1 is x, which actually got more complicated, didn't it? Like 1 was 1 and now it's an x. Like, so we start going, oh crap, you know, is this going to get worse? Well, let's take the derivative here of the u. So the derivative of the u, you have to use what we've already learned, right? About derivative inverse sine. You bring up your formula sheet. You know, if you don't remember it, you bring up your derivatives of your inverse trig functions, which are right here. And we're talking about this right here. So we're going to be using that formula right there for the derivative of sine inverse of x. We're going to do it right here, but do we have x? We have something other than x, right? Pi x, right? Pi x inside. So I have to use chain rule. 1 over the square root of 1 minus, and now in parentheses, pi x, that quantity squared, times now the derivative of what was inside of here. What's derivative of pi x?
Pi.
Pi. Pi is like a number, right? So derivative of 2x would be 2. So derivative of pi x would be pi. And then I'd have to tack on that dx to the outside. At this point, we're going to use the formula now, right? Ultraviolet minus voodoo. And when we look at voodoo here, we're going to need to put that in the new integral, right? That piece is what goes in new integral. That doesn't look very good. It looks actually pretty terrible. But let's just do it. This was our only choice, right? We didn't have any other choice. So let's just go with it. That's why I'm calling this one, you know, a not so obvious integration by parts. It doesn't seem like we're really achieving anything here, but let's see what happens. So this becomes equal to, all right, ultraviolet, we're going to multiply those two together first. So I'm going to write that as x inverse sine of pi x minus space between or here, integral, all right, voodoo. So v is x, there's my voo, and then now my du is 1 over the square root of 1 minus, should I show this to you now? Yeah, well, yeah, I'm trying to figure out. This is a key step, and I don't know if it's a natural step. So I'm going to square the pi x, which becomes pi squared x squared. And I'll show you in a minute why I did that. Let's continue though. There. That's voodoo. Any questions on that setup? Ultraviolet minus voodoo. Voodoo looks bad, right? The integral of voodoo looks bad. I'm going to rewrite the problem. X sine inverse pi x. I do have a constant here, pi. I'm going to pull that constant out. Minus pi integral. And the only thing left here is I have an x on top of a square root of 1 minus pi squared x squared dx. And I know when you look at that, you're like, oh my gosh, this looks horrible. Like, what's going on here? The pi squared is scary. We've got to figure out what the antiderivative of that is. And like I said, it may look, you may look at that and you're like, I have no idea. However, we've already covered the technique that you need to do this. You're actually going to be tested on that technique on Thursday. So who sees it?
It's a U substitution, right?
Yeah,
What's
U
the-
substitution
okay, so
of the
what's
entire
the U
bottom inside the square
substitution?
root.
What is the U substitution? This is a basic U substitution problem. So what is it?
U is 1 minus pi squared x squared.
1 minus pi squared x squared. So remember basic U substitution, we're trying to look for something and its derivative. And the derivative just needs to be in the numerator and not trapped, and it's okay to be off by a constant. So notice that if we chose this to be the u, the derivative of u would be, well, the derivative of 1 is 0. What is the derivative of this piece right here? We'll have a negative. What about the pi squared?
It's constant.
It's a constant, so it comes for the ride. Times, okay, what's the derivative of x squared?
2x.
2x. So I put a 2x here, dx. And I'm saying, do I see that? Do I see that derivative, du? Do I see it in my integral? It needs to be in the numerator and not trapped. I have an x dx, don't I, in the numerator? And over here, I have an x dx. I'm just off by a constant. This is a constant, right? Negative 2 pi squared is a constant. So I'm off by that much. So what I'll do now is I will get rid of that on the right-hand side by doing 1 over negative 2 pi squared du equals x dx. And now those two things match exactly. Who has a question? Anybody?
Why wouldn't the negative pi over 2 just cancel out again?
Cancel out with what?
Like when you're getting the derivative of that.
When I'm getting the derivative.
'Cause
Oh,
they're
why
considered
doesn't
as
it like go to
constant.
0?
Yeah, since it's a
Well,
constant.
because it's attached to a function. So it's like if you're trying to take derivative of 4x squared, right? This just becomes 4 times 2x, which is 8x.
Oh,
What you
okay.
don't do is you don't do the derivative of each of these separately, right? You don't say it's 0 times 2x, because then it would just be 0, right? I don't know if that's what you're asking.
Yeah, sorry, I
Okay.
forgot about that part. Thank you.
If the constant's by itself with no variable, the derivative is 0. But if the constant's attached to a function, then it comes for the ride. All right, let's see where we are. I've got minus pi. Okay, this integral, everything in blue, right? Everything in blue is going to be replaced by this. And then everything in green is going to be replaced by u, right? So let me write out what we'll have. We'll have 1 over the square root of u, that's the green part. And then now the blue part, which is 1 over negative 2 pi squared du. If you're having trouble seeing what I did here, I took this integral and I rewrote it as 1 over the square root of 1 minus pi squared x squared times x dx. I slid that x out to the side over here with the dx so that I have exactly x dx there, and I have exactly 1 over the square root of u. And then just replaced everything. Before I go try and find an antiderivative, let me clean this up. All right, this is a constant and it can come out of the integral. And it's a negative and I have subtraction out there, so it's going to come plus. And then I have a pi out front. And on the bottom, I have a pi squared. So one of those pi's will cancel, right? I still have a 1 on top. I still have a 2 on the bottom and 1 of the pi's. So that's what happens when I pull this whole thing, the box right here, when I pull it out front here. And now in the integral, I have, what am I going to do with that? Should I leave it as 1 over the square root of u?
Negative 1/2.
Yeah, write it as u to the negative half. That way we can use the power rule, right? Which was one of the first rules we learned when finding antiderivatives. Okay, I'm ready to take the antiderivative of this. So the power that we have here, this is like the n in the formula. That's like our n. So we're going to add 1 to that. So out front, we put 1 over 1 plus -1/2 is a half. And then u raised to the 1/2 and then plus c. So what you see in red there is the power rule on this u to the -1/2. We're almost there. X sine inverse pi x, okay, plus 1 over 2 pi. That flips and becomes a 2. And then u to the half is really the square root. And then u, don't forget what u was. We did our substitution up here. U was 1 minus pi squared x squared, and then plus c. And maybe the only other thing to do is cancel the 2's out right there. So I get to cheat here. There we go. All right, let's get some feedback. What do y'all think? This is our first problem that we've had where we had to do integration by parts, then u substitution, then what else? Power rule, right? All 3 techniques were used, all 3 of those skills. What do y'all think?
I'm just like, how do you know when you're doing integration by parts like this, like a more complicated one? How do you know when you're like gonna have to use substitution? Like,
Well, your new integral, right? We went through the integration by parts. We only had one option on setting this table up. There was nothing else that we could have done. I mean, that would be something key that you have to see. If you let dv be the sine inverse of pi x dx, and then you try to do the antiderivative.
oh no, I meant like when you get to the part where you're gonna have to use substitution inside of it, how do you, what's kind of like the giveaway that like, hey, I have to make a use substitution, you know, when you, in that middle part?
What gave it away is that I saw it. Like I had to see, I don't know, who was it? Or Josiah, right? Said that? I think it was Josiah who said use substitution, right? Are you there, Josiah?
Yes.
So can you explain how you knew to do use substitution?
I just saw that something was trapped in the denominator, so assumed the substitution was the answer.
Yeah, I mean, this is the part that's so hard to teach, like, because it's not like a, when you see this, do this. It's like, you just have to see that it's a u substitution. You've got to be, so you're constantly, when you're looking at integrals, you're constantly looking for, you know, hey, integration by parts. Can I do my table here? Oh, is it just a basic u sub? Do I see something as derivative? Hey, is this just power rule? Hey, is this just something I know from Cal 1? The antiderivative is simple. Like you're constantly, your brain is constantly looking for little signposts that kind of, I don't even know. It's hard to explain because it's hard to teach that sort of intuition. You just need to know you need to be constantly looking for things. There's not like one thing that's always going to raise a flag for you and say, okay, now you go down that road. Does anyone else have another sort of, I'm seeing some comments here. U sub is for quotient rule, integration by parts for product. No, we can't generalize it that easily. Because anytime we see a product, that does not mean that you use integration by parts. Anytime we see a quotient, that does not mean you do U sub. It could be, but that's not always the case. Trust me, if there was something I could give you where I could say, hey, this is always the case that you do this, then I would give that to you. We do that in Cal 1, right? Anytime we see a product, we do the product rule. Anytime we see a quotient, we do the quotient rule. And I told you at the beginning of this class, when it comes to antiderivatives, things are not that simple. There's not a rule that you always do every time. Everything is about you rolling through this index of techniques in your mind. At every point in the problem, you're constantly thinking anything is in play. And that makes it hard. That makes it hard because how did I even know that this was going to turn into a U sub problem? I really didn't know. I just cranked away and it worked out. So, I mean, I wish I had better news and a better answer for you, but I promise you that you get better at this with practice. I told you in the beginning, like you're going to get things wrong more than right. And then eventually you start getting things right more than wrong. And you just continue and continue. I believe I have a thing on our, if I'm not mistaken, I have something on our.
On Thursday, are we gonna see a problem kind of like this where we're gonna have to do both in one
I
problem?
think this one is going to be on, this type will be on the next test.
Okay.
Yeah, because you do need the time to suffer through homework problems like this. Well, you know what? I don't have it here anymore. I used to have a quote on the front page of all my classes or all my calculus classes. I don't have it anymore. Oh well. I used to have a quote that said, don't practice till you get it right. Practice till you can't get it wrong. There's a difference between those two things, right? You don't want to be doing your homework saying, oh man, I finally got one right. You want to be doing it until you're like, give me one. I'm not going to get it wrong. That it takes a long time to get to that point. Trust me, when I was a Cal 2 student, you know, it was a long grind to get to a point where I felt comfortable. And even then it was uneasy comfort, right? So I don't know if I'm answering your question, Ethan. Just persistence here. And don't get discouraged. It's going to be hard. It's going to be tough.
I have a question.
Yeah.
So, I mean, I actually find that like I saw the use substitution and I saw we needed to use integration by parts for this problem because there was no, like the derivative of something wasn't there. But
Yeah.
like for the first one, like there are problems where we had the x sign of 10x dx, like
Yeah.
if you made u 10x and like you got your derivative as like 10 dx, like I think it's kind of harder to figure out because couldn't you like set your u equal to x or something and then like because there were some problems where it was like, oh, the x is separate and you don't have a u for x, and then you basically make your u like equal to like x. Like
Yeah,
there
I
was a
got you.
problem. You kind of know what I'm saying?
Yes, I do. I think know what you're saying. Let's do it and let's see why this won't get us anywhere.
Okay.
So if I do this, right, u is equal to 10x, take the derivative, I just get 10 dx. So I can see here that I have a dx here, that'll match this. And so I need to scale that by 1/10 so that it matches exactly, right? So that dx and dx match. And then as far as the 10x, that's going to be our u, right?
Yeah.
And then the only thing really left for me to figure out is what's x.
So
But I
why?
can take this first equation. Go ahead.
I was just saying, yeah, like why can't you just make your u like 1/10 u equals x? Because I know
Yep,
there.
you can do that. Perfect.
Okay, so you can do
Okay,
that.
so let's do it. Let's now replace everything and let's see what we have. So 1/10 u, right? Sine u times 1/10 du, right? That's where we are. Everyone see where all that came from?
Yes.
That's your yellow, that's your blue.
But you're
That's
still
your-
gonna have like that whole product rule problem, right?
Yeah, see,
Okay.
even if
You
we
would
pull
still
out the
product
two
rule.
1/10 as a 1/100, do you see you still have u, sine u, du? You see
Okay.
that you still have the same sort of thing we had up here. We had a linear expression, right? And then we had sine of some other linear expression. And we couldn't do anything with it, but now what are we left with? A linear with sine of a linear again. Like, yes, it looks different, but we have the same problem that the U substitution didn't make it better, right? It didn't make it easier, just made it look a little different.
Okay. So you can try use substitution, but
Oh,
if
yeah.
you're still left with the product or quotient rule, then you're like, all right, to do integration by parts.
Yeah. I mean, this is, y'all are asking questions that really gets at the heart of what makes this class so difficult. Is that when I'm sitting here saying we're going to use integration by parts, I'm doing that knowing that nothing else is going to work. But the only reason I know nothing else is going to work is because I've already done this. I've already tried that and it didn't work, right? There's nothing, there's no, if this is your first time seeing a type of problem like that, you might try the U sub first and then you get stuck and then you go, okay, well, I better try something else, right? In class, I just don't have the time to run through every single little thing, or else we'll only be able to see like 2 examples, 3 examples. You know what I mean? So, but try it, right? I mean, you want to try it. The more things you try, the better you're going to be for it, because you're going to start to see like, okay, I've done that before. It didn't work. I wound up using integration by parts. Let's just do that. All right. We're on the journey, okay? Y'all are on this journey. This is Cal 2. This is the journey of Cal 2. It's interesting. It's like a puzzle, right? It's like this puzzle. You're trying to figure this out. You're trying to figure out how to win, right? You're going to try and win. And
Can I say something about the last problem that we did?
yep.
I think I see it, well, not that one, the other one, the one that we do, like, yeah, that one. Like if we do like when we do the use substitution, if we do integration by parts, it's not gonna get any better because we're gonna have like x to the probably the square, then the root's gonna actually, make another power. It's gonna actually get worse instead of getting better.
Say that again.
Yeah, like what we did use substitution, where we
Yes.
have the integral of x over the square root of 1 minus pi square
Yep.
x squared dx. If we do integration by parts on that one again, it's not gonna get any
Oh.
better.
Ooh, yeah. Integration by parts on that again would be a
Yeah, it's gonna get worse
disaster.
actually.
It
So
would
I
be
guess the
horrible.
only yeah, so
it would be horrible. Yeah, because I think you've already kind of thought through what it would be like. What's going to be your U? What's going to be your DV? And things will get really, really bad.
Yeah.
Yeah. Do you all see how important it was for me to actually take this pi x and actually square it? Do y'all see that helped you see the U substitution? Because by having this, you had an x squared, right? And the derivative of that was x, which you had up here. You're off by a constant. If I had not squared that, you may not have seen that, or it may not have been so obvious. And I told you when I was doing it, I'm going to do this and you'll see maybe like why, or I'll explain why. That was a little subtlety of the problem that I kind of glazed over, but it's a critical step. Okay, let's get to another problem. I mean, it's, we're just on this journey, right? We're just getting started here. All right, take a look at this one. I mean, you almost maybe want to let that be U, right? T squared, the derivative of that's 2t. Inside I have beta t. Oh, that's a variable. Okay, beta t. I'm off by a constant, right? If I did U sub, but that derivative is trapped inside a cosine, right? So I would not want to do this. I would not want to do this because the derivative of that t squared is trapped. So that's off the table. Also, just so we know, this beta is a is a constant, but it's a variable. Like it's some number, but we don't know what it is. So for the sake of just making it simple, just imagine that beta is like the number 5. All right. We're going to treat it like a constant the whole way through. All right. So now I start thinking, okay, integration by parts, right? If I do integration by parts, if I choose this to be u, let's say I let that be my u and I let everything else be dv, then do you agree that the derivative of u would be better than what it is right there? Like the t squared would then become 2t. So the powers come down, and that's perhaps a good thing. Yeah.
Yeah.
And then we have to be able to take the antiderivative of the cosine beta t, but I should be able to do that because that's the same as like taking the antiderivative of cosine 5t. So I'm liking the integration by parts right now, at least as taking a swing, right? We're buying a lottery ticket. We may or may not win, but we won't win if we don't buy the lottery ticket, right? So we've got to set up the table. We've got to at least be willing to try something. Right, I differentiate down, du is 2t dt. And then the antiderivative of this is v. And that is 1 over beta sine beta t. So like I said, that beta is like a number, like 5. So if I'm taking the antiderivative of cosine 5t, I've got to scale that out, 1 over 5. So I have to put 1 over beta sine beta t. No negative, right? Because the antiderivative of cosine is positive sign. Questions? Okay, ultraviolet minus voodoo. Watch the way I write this. 1 over beta t squared sine beta t. All that is these two multiplied together. And then I rearrange the order because it's multiplication. Minus a little bit of a space in between. Now I'm doing these two multiplied together. Can somebody tell me what constant can come out?
2 over beta.
2 over beta, right? A 2 comes out and a 1 over beta comes out. So I'm going to pull it out as a 2 over beta. Good. And then all that's left in there is I have a t, right? I have that t right there. I have a dt. I'm going to stick the dt in the back. And then I have the sine beta t because the 1 over beta already came out. So sine beta t. All right, that's where I am. And I look at that integral and I'm like, shit, I can't do that integral either for the same reason I couldn't do the first one. However, there's nothing stopping me from doing integration by parts again. What would kind of be the hint, or what would be the thing that kind of tips you off that you should probably do integration by parts again?
The derivative of t is 1 dt.
Exactly.
Product.
Yeah, not the product. The product, don't let the product be any indicator of integration by parts. Right? You'll get yourself in trouble. Definitely as we move on in this class, if you look at every product and start thinking integration by parts, it's going to be a disaster. What you're wanting to see is the fact that if I do integration by parts again, and use that t to be my u, in the new integral, its derivative will be a 1. Which is good. It's like things are getting easier, right? Each time I'm doing this integration by parts, because this was t to a power, the first time I did it, it became a t. And then the second time I do it, you're going to become a 1. So I'm kind of like chipping away at the power.
And
So
you kind of like infer that, like, I know you said like product don't correlate that to integration by parts, but because like, can you just kind of eliminate u substitution? Because if you try to do a quick u substitution here, you're like, oh, that's a product rule, it's not really going to fix it.
there are problems that are products that basic U substitution would work for. So I can't say that. Like if I gave you this problem, you might look at that and say, oh, that's integration by parts because I see a product. But this is basic U substitution because what is the derivative of that?
1 over
Just
b over
lower b times 2t.
Yeah, so if I just let U be beta t squared, the derivative of that would be 2 beta t dt. Oops, dt, right? Everyone see that? That's a derivative of beta t squared. Do you have that? Well, I have t dt, don't I? I have t dt. I'm off by how much?
2
beta.
beta.
That's a constant. So I'm off by a constant. So I'm going to do basic U substitution here. You see what a subtle difference, like it's just that square that made me that gave me the ability to do that problem with U sub. The problem we're looking at, right? It's not squares to the first power. And so I don't have the ability to do U sub, right? But the integration by parts took that power from t squared down to t. So if I do it again, it should take that t to a 1. Not only that, the antiderivative of sine beta t is going to be something with a cosine. And so I'm going to have a 1 and a cosine together in my new integral. And that I'm happy about. Because then I can just do the antiderivative cosine. The other piece was a 1, so it should work. Let's let u be t, and then dv, let's let it be the sine beta t dt. And then du would just become 1 dt. Remember, I'm using the variable t here, so don't be all of a sudden putting dx because that wouldn't make any sense. And then this is negative 1 over beta cosine beta t. Any questions on the table where any of those pieces came from?
Why do we use a sign for dv instead of for u?
Instead of
how do we
what?
How do we determine which one to use for t, or which one to use for u and which one to use for dv?
Well, you have to think about what the new integral is going to have in it. So what if you did it the other way around? What if you let this be your u and you let this one be your dv? In the new integral, you'll have the derivative of that. What would the derivative of that involve? Cosine,
Chain rule.
right? Right? Cosine? But
Yeah.
what would the antiderivative of this be? Something with what? Antiderivative of t would be
1/2 t squared.
1/2 t squared. So now in your new integral, you've got a 1/2 t squared and you've got a cosine beta t. I mean, there's constants in there too, but do you want that? Do you want a new integral that's going to have t squared in it? Well, didn't we just come from that? Didn't we have a t squared? We did integration by parts and we got it to a t. Who asked that question? About choosing which one?
Oh, I did. I'm sorry.
Okay, do you understand what I'm saying or no? Like, are you following?
Yes.
Okay. That is like a fundamental point. I want everyone to understand. It's not we really want to try and see down the road what the voodoo looks like in the new integral, right? Ultraviolet minus voodoo. What does that new voodoo look like? And are we happy about it, right? So when I was here, I was thinking to myself, if this is u and this is dv, the derivative of that will be 1 and the antiderivative of that will be cosine. I'm good. I'm pleased to have that. Let me keep going. Okay, so what I'm gonna do now, you have to be really careful with this. Let me put this in a different sort of. This entire integral right there, I'm doing integration by parts on that integral. Right after the -2 beta, I had a new integral, which I had to do integration by parts a second time on. So I'm going to put in brackets here. I'm going to write down ultraviolet minus voodoo again, but off of this table instead of the previous one. So ultraviolet, I'm going to multiply these two together. Watch how I place my constant out front, -1 over beta, then T, then cosine beta T. That's ultraviolet, minus space integral, and now my voodoo, which are these two multiplied. I can pull a constant out, can I? That -1 over beta can come out. So that should turn into a +1 over beta. And then what's still in my integral?
Cosine beta t dt.
Cosine beta t dt. And that I am happy about because I've gotten rid of the t, right? It was a t squared out there in front that was causing a problem. Then I got it down to a t. Now the t's gone and I can find the antiderivative of that. I realize this is a lot of writing. All right, I'm ready to take the antiderivative of cosine of beta t, which is 1 over beta sine beta t. Now I should put a plus c here, but it doesn't matter where I put the plus c, so I'm going to close the bracket and just throw a big plus c on the very outside. One more step. I'm going to distribute the -2 over beta through and get rid of those brackets. This will be my final answer. 1 over beta t squared sine of beta t plus, because when I multiply this negative and negative there, it becomes plus. And then I'm going to have the 2 on top, 2 times 1, and then beta times beta is beta squared. And then I have the t cosine of beta t. That's my first multiplication. Then my second multiplication, I'm going to have a minus, I have a 2 on top, and I have 3 betas being multiplied together. Beta, 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 beta cubed, and then a sine beta t, and then plus c.
If we didn't make that, if we didn't factor that 2b in, or distribute it, would the line above your final answer, would that still be acceptable?
On a test, I'd be okay with the line above. On a test, I would, because time-wise, if you're trying to just save some time, you've gotten to the point where you've given me the antiderivative. That's good. That's good for me.
Cool.
But that's something everyone should be able to do, right? That's not like a crazy thing. All right, how are y'all feeling? It's a little humbling, isn't it? We've done 3 problems. Right, that was an example of a problem where you had to do integration by parts twice, right? So it's a repeated integration by parts. All right, the next one, classic example. Every Cal 2 student needs to see this problem because it's just weird. I call it the rabbit out of the hat, which implies it's going to be magic, right? All right. So we look at it and we go, okay, basic U substitution. We may mess around with it. nothing's gonna work. The only other thing we have is integration by parts, right? That's all we've got. But if you start to catch on to integration by parts, you start to realize that you're going to let one of these be u, right? Let's just say that one's the u and that one's going to be the dv. Let's say we do that. I've told you, I really want you to be thinking about down the road, about that new integral, right? That new integral, voodoo. What's going to be in that new integral? If I let u be e to the 2x, what should I expect to see in the new integral? The derivative of that, right? What's the derivative of e to the 2x?
1/2
E to
each of the
2x.
2x.
Careful, not the antiderivative, the derivative of it.
2 each.
2e to the
2 e to the
2x.
2x. So I should expect to see an e to the 2x there, right? There will be a 2 in front of it. See, I don't even care about the 2 because the 2 can come out of the integral, right? So I'm starting to think, okay, when I do this derivative, it's going to have an e to the 2x in it, right? Like just generally speaking, I'm going to still have an exponential function in there, right? And then I need to get what v is, which is the antiderivative of cosine. What's the antiderivative of cosine?
Sine.
Sine. So I'm going to have a sine there, right? That's what's going to be in my new integral. Am I happy about that?
No,
No.
No, why?
you didn't get anywhere
I
really.
didn't get anywhere. All I did was kind of like swapped out the cosine for a sine, right? I still have an e to the 2x, I still have a sine. So it's not looking very promising, right? What if I switch it? What if I do it the other way around? What if I take it and I try the other way, where I go, all right, let's let the e to the 2x along with the dx, those two together, let's let that be the dv and let the cosine be the u. What should I expect to see in that voodoo new integral?
Sine
Well,
into e to the 2x.
yeah, this is the derivative of that. The derivative of u is going to sine x, right? And then if I take the e to the x dx and do the antiderivative of e to the 2x is still going to have an e to the 2x in it, isn't it?
Yep.
So either way, my new integral has e to the x in a sine, or e to the 2x in a sine, right? So it doesn't appear that integration by parts is going to get us anywhere on this, because I still wind up with an e to the 2x with the trig function, which is what I've started with, e to the 2x with a trig function. Sine, cosine, doesn't really matter. Any questions on why this like doesn't look very promising? Everyone gets why this doesn't look that promising? Okay, well, you know, sometimes we just gotta like see what happens, right? So I'm gonna do it, even though I'm not real optimistic about this. I'm going to do it. And I'm just gonna go back to the first way. I'm gonna call that the u, and let's let this one be the dv. U is the e to the 2x, and then the dv must be the cosine x dx. The derivative of u is, why is that acting like that? The derivative of u is 2e to the 2x dx, right? Because when you take derivative e to the 2x, it's itself times the derivative of what's up here, which is 2, and I just slap that out front. And then the antiderivative of cosine is sine. All right, so this new integral becomes equal to ultraviolet, these two multiplied, e to the 2x sine x, minus, I'll leave a space, voodoo, which is these two multiplied. So I do have a 2 I can pull out of there. E to the 2x sine x dx. As a little side note while you're thinking about this for a minute. A lot of times people ask, why do I need to take calculus 1, calculus 2 if I'm going to be this or if I'm going to be that? I hope that by seeing this, you're starting to see that this has more to do with your ability to think critically about things and to become a better problem solver than it is about you actually being able to find the antiderivative of a function. This is about persistence. This is about intuition, about developing those things and getting better at them. So yeah, little sidebar there. All right, so it doesn't look like this got better, right? Doesn't look like it got better. If I did integration by parts again, what would happen? Like if I tried it a second time on this, on the piece right here,
Literally the exact same thing.
You would
Yeah,
get the
you'd go
original
back to
function.
your-
I go back to
Yeah.
the exact same thing, right? Which initially doesn't appear to be something I should do, because like, then it seems like I'm just going to be going in circles. But it works, okay? It doesn't look like it's going to, but we're going to do it. Just follow me through this. It's fine. I said it's the rabbit out of the hat. We're about to pull a rabbit out of the hat here. So I'm going to choose my u to be the same thing, the e to the 2x, and I'm going to let the sine x dx be my dv. And I'm just going to play this game again. Sine x dx. Now, the derivative of e to the 2x is itself times 2, which we did a little while ago. And then the antiderivative of sine is negative cosine. Oh, it's so important that you remember that that's negative. Actually, this problem falls apart if you forget that. All right. Here we go. This is equal to e to the 2x sine x minus 2 bracket. Okay, everything in this bracket is this integration by parts thing, right? So we have another ultraviolet minus voodoo over here. Ultraviolet, those two multiplied, I'm going to write that as negative e to the 2x times cosine x. So I pulled that negative that was in front of the cosine, just slapped it in front of the e to the 2x. Minus, I'm going to leave a space, integral, and now I'm going to do voodoo. What constant can I pull out of there?
-2.
-2. So is everyone okay with me pulling a -2 out of there and making this a +2? Is that all right?
Yeah.
Okay, and now inside this integral, we've got e to the 2x cosine x dx, and then it's all sitting inside this bracket. So you look at this and you're like, well, crap, man, I'm back to where I started. My original integral was e to the 2x times cosine x dx, and now I'm asking myself again, what is that? So initially, it does not look like we've gotten anywhere. But watch this next line. What I'm going to do, this is the rabbit coming out of the hat here. I'm going to take my original problem, right, and I'm going to write it down. The integral e to the 2x cosine dx. What I'm saying to you is that that's equal to, and now what I'm going to do is I'm going to write all this down, okay? But I'm going to distribute this 2 through here, sorry, that -2 through. So it's going to be e to the 2x sine x plus 2 e to the 2x cosine x, right? Because negative and negative was positive. And now -2 times +2 is going to give me -4 of these integrals that I have no idea what it is. Questions on that line? Who sees it? Anyone see it?
Do we add the integral to both sides?
The integral we're looking for, the integral we're trying to find appears over here, right? But the difference is that on the right side, I have -4 of them, right? So here I have one of these integrals. One of these integrals is equal to all of this -4 of the integrals. So I am going to add 4 of these integrals to both sides of the equation. That's weird. On the right side, it goes away.
I'm
And on the
sorry.
left side, one of these integrals plus 4 of these integrals is how many of them? One
I'm
apple
sorry.
plus 4
You
apples.
lost me.
5 integrals.
Where did I lose you?
When you started adding integrals together.
Okay, so what if I wrote this down? X equals 2 minus 7 minus 4x. And I ask you to solve for x, what would you do?
I would first combine the 2 and the 7, then move
Okay,
on to
you
the
put
other
those
side.
two
and divide by
together.
4x.
That's some number, right? And then you would want to get your x's on one side.
Yeah,
So you would add 4x to both sides.
yeah.
Okay, that's basically what I'm doing here. It's like
That's so
this
crazy.
this is something, right? Who cares what that is, right? But I've got -4 of these things. This thing in yellow is like an x. Treat it like an x. I have -4 of them, and on this side I have 1 of them. So I'm going to add 4 of them on this side. They'll go away, and I add 4 of them on this side, and they add together to become how many of them?
That'll be 5. But
5 of them.
I guess like I'm more confused on how do we get to the point where we're adding this? Because I was following along and then like now I'm just like lost.
We were going through all this work, and then we got to a point where like, crap, well, the integral that we have here is the original integral, right?
Uh-huh.
And I said, okay, let's just rewrite where we are. Let's write down the given problem, right? This was the given problem. I put it right here. That's the given problem.
Mhm.
And where we were is we had said that that's equal to, and then this is all the work that we've done. We've done integration by parts twice.
Yeah, yeah. I have
And
all
then I'm
that.
saying, well, wait a minute. Hey, whoa, these are the same integrals, but I have -4 of them here and I have +1 of them. So I'm going to get this integral off this side of the equation by adding it to both sides.
Okay.
Now,
Okay,
if you don't bring this down, right? If you don't bring this down, then this doesn't happen because you don't have an equation. You have to
Yeah.
bring that down from the beginning and say that original problem is equal to this now. And
So
then move
if-
it around.
If you're stuck like we've done this twice now, we're not getting anywhere, you would just bring down the original problem and kind of just like go from there instead of just doing it over and over and over again.
Yeah, so I said this is a classic problem. What makes this a classic problem is that this is an example where you see that sometimes if you do integration by parts multiple times when it looks like you're getting nowhere, the integral that you're looking for might appear on the other side of the equation. And if it does, well, the integral you're looking at may appear somewhere in your answer. If that's the case, bring down the original integral, create an equation, and then start working with it like an equation, moving one thing, things to different sides.
So even though we normally forget about that left side, like
Yeah.
it's in actuality, it's almost like a gigantic algebra equation. It's just you can
Now it is,
that's
right?
the-
Now it is. Yes, exactly. Now, up to this point, we've never had to do this, right? We've just said, here's the original integral equals this, equals this, equals this, equals this, box our answer, and we're done. We've done this and we've said, okay, here's the original problem, equals this, equals this, equals this. And we said, crap, where we are has the original problem. So let's just bring it down and just say, this is where we are, right? The original problem is equal to this, and then start working with it like an equation. All right, so I put those together. I have 5 of them now. And notice on the right-hand side, I no longer have any integrals, right? What do you think my last step is?
Divide by 5.
Divide by 5. Divide everything by 5. Both sides of the equation, divide by 5. So I'm gonna write this as 1/5 e to the 2x sine x plus 2/5 e to the 2x cosine x. Now, there is one little catch to this method. Because we treat it like an equation, we kind of lose sight of the fact that this is an antiderivative, so we have to remember that there's got to be a plus c out here. There it is. That's pretty cool. The rabbit out of the hat is seeing that the original integral appears and that you can move it to the other side. That's us kind of like going, whoa, there it is, magic. Now we've got it. I want to do something real quick with this. I'm going to check our answer. I'm going to take derivative of this. I'm going to move fast. I have addition, so I'm going to do two different terms. I'm going to do product rule here and product rule here. Actually, you know what? Yeah, I'll do it. Okay, so I take derivative of all this first. This is 1/5 times 2e to the 2x. That's the derivative of the first one, times the second one, plus the derivative of the second one, which is derivative of sine, which is cosine, times the 1/5 e to the 2x. All right, all that plus, now I'm doing product rule on this. Derivative of that is going to be 2/5 times 2e to the 2x times cosine x, and then plus the derivative of cosine, which is negative sine x, times the 2/5 e to the 2x. This and this cancel completely. Those are the exact same things. And these two are like terms because they both have cosine, cosine, e to the 2x, e to 2x. So the only thing you have to do is add their coefficients. This is 1/5 and this is 4/5. So if you add 1/5 and 4/5 together, you get 1. You get 1 e to the 2x times cosine of x, which is the original integrand right there. So it works.
Astonishing.
Yeah, it works.
That right there is astonishing.
Well, this is the power of the integration by parts, right? I mean, it's humans' attempt. It's our attempt to try and undo the things that Cal 1 does, the product rule quotient. We're trying to undo that stuff, and it's not simple. It's not simple to do that. Like there's no human being that looks at this problem and just tells me the antiderivative. Nobody does, right? Nobody does. You have to grind this thing out. All right. Let's see, 20 minutes. I did this one in class last time. We did the antiderivative of natural log of x. I did that in class, and I allowed you to put it on your formula sheet. Remember? I did, right? Someone please verify. Did I?
Yes.
Yes. Okay. All right. All right. I'm gonna step away for just a minute. I want you to think about this one, and I'll be back and we can talk about it. All right, here we are. Sorry about that, but I also wanted to give you a little bit of time to just mess with it. So any progress? Anybody want to share what they've tried, whether or not it's worked or not, regardless of it's worked or not?
I've tried setting u as e to the square root of x and dv as 1 dx.
Okay, so you tried integration by parts. You let u be e to the square root of x because you really don't have much of a choice, right? I mean, that's kind of the only thing you can do. dv would then have to be what?
1
dx.
1 dx, right? That's the only option you have. So then v would be antiderivative is x. And then here we're going to have chain rule. So derivative of e to anything is itself times the derivative of what's up there, which is 1 over 2 square roots of x, right? That's the derivative of the square root of x, dx. All right. I mean, we're getting somewhere, right? I mean, we're playing the game. So let's write things down. We're going to have ultraviolet. So this integral becomes ultraviolet. I'm going to write that as x e to the root x minus, I'm going to leave a little space to pull out a constant if I need to. Do y'all see what constant I can pull out when I do voodoo?
1/2.
A half, yeah. Everything else I'm going to just leave as is. E to the root x times, I pulled the 2 out of the bottom, so I still have a 1 over root x. And then times, I have an x dx. Anyone have a question on where I am at this point? The only thing I'm going to do now is I can actually clean that up, right? That is really like x to the 1 over x to the half. That's really x to the 1 minus a half, which is x to the half, which is the square root of x. So I can rewrite this as the square root of x times e to the square root of x dx. All right. Have we made progress? What do you think?
No, it kind of looks worse.
Kind of looks a little worse, doesn't it? If I did integration by parts again, ugh, not sure it gets better. Joshua, had you gotten this far, or were you?
This
I'm
is
just sorry,
as far as I
Josiah.
got.
I'm sorry, not Joshua.
This is as far as I got.
As far as you got, did anyone try anything different? So before I proceed with this, let me say something. Please remember that I'm just the messenger, okay? Like, I realize what I'm about to show you is going to seem a little bit demoralizing because you're going to be like, well, how in the world would I have thought to do that, right? That's part of what I'm trying to show you here is, you know, I was sitting where you are right now, and you know, I understand the frustration, but you got to be willing to try things that don't even seem like that they're very natural. You need to be willing to take that step. So I'm going to start the problem over. All right. Now, there might be a path through with this. That might go if we grind it enough, it might go. All right. But I'm going to do something that seems unnatural. I'm going to make a u substitution first. U is the square root of x. But I told you with u substitution, you're looking for something in its derivative, right? And the derivative has to be in the numerator, it can't be trapped, blah, 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 blah. Well, I don't see the derivative of that anywhere. Do you? Not there, right? So you're sitting here going, well, that didn't really, I shouldn't do this. Well, watch. If I take the derivative of this, I get 1 over 2 root x, right? That's the derivative of that, dx. And I'm looking everywhere for it. I can't use this. That's already u. So do I see that anywhere? No, I don't. Now I do see a dx, right? Great, but am I off by a constant? No, I'm off by an entire function, right? If that was just 1/2, I'd be happy, but I'm off by 1 over 2 root x. Wait a minute though. Isn't root x just u? Isn't it? Isn't that what u is going to be? In other words, I could rewrite this 1 over du equals 1 over 2u dx. Now the dx matches. Now multiply both sides by 2u and get dx by itself. This is actually okay to do because do you see that the thing I'm going to replace dx with has u's in it? It can't have x's in it, but it can have u's or numbers, right? It can be a constant or as long as my integral goes from x's to u's, I'm okay. So when I rewrite this problem, it's integral e to what power? U, okay. And then times dx, but dx is 2u du. Then I'm going to pull a 2 out and get u times e to the u du. I'm just going to pull the u out front.
Can you explain what you did with the derivative again? You kind of lost me.
Okay, so at this point right here, I looked at it and I said, crap, I have an x here, right? So I'm off. I can be off by a constant, but I can't be off by like an entire variable. And so what I did here is, here's another way you could have done it. Multiply both sides of the equation by 2 root x, right? If I multiply 2 root x here and 2 root x here, they cancel. And then on the left side, I've got this, and the right side, I've got that. So I'm replacing dx with this thing right here. Normally, that would be a problem because I can't have x's in here. Whenever you rewrite your new integral cannot have u's and x's. It's got to be all x's or it's got to be all u's, one or the other. But I'm using the fact that the square root of x is actually u. So I can replace that with u and becomes 2u du is dx. Did that help or no?
Yes.
Okay. So now I'm looking at this integral, and I'm not sure if it's better, right? You could argue that's not necessarily better, but this can go with integration by parts. This will work with integration by parts. Why? Well, I'm going to make a table, right? And I'm supposed to pick a u and pick a dv, right? U dv. I can't use u dv anymore because I've already done a substitution with u. So I can still call this dv, and then I can integrate up to v, but I can't use u again I have to use a different variable. So I'm just going to make up a variable. This can be w. So I'm going to replace w with u, and this is going to be my dv. W is u, dv is e to the u du. And now I'm just going to play that same game. Differentiate down, integrate up. dw is du, and the antiderivative of e to the u is itself. Is this good or not?
Do we need to multiply e to the u by u prime
Where?
for v? Oh wait,
No,
no.
because you're just taking the
can handle it.
antiderivative. You're taking the antiderivative of e to the u, which is itself. If you were taking derivative, then yeah, you would have to multiply times derivative of u, which is this line. Do we like what we're seeing here? Like, is this doable now? See, I can't use ultraviolet minus voodoo anymore because I'm using W instead of U. But we still have the same idea that we're going to multiply those two together. So let me go ahead and just write this down. We have a 2. Okay, bracket. Ultraviolet minus voodoo. But really what I mean is these two multiplied. So U e to the U minus a space integral. Now I'm multiplying these two together. There's no constant that comes out there. So all I have there is e to the u du. And that is an integral that I have no problems with. The antiderivative of e to the u will be itself again. So we have 2 u e to the u minus the antiderivative e to the u is itself. Add a plus c because I took the antiderivative. Oops, and just put that. I'll put that in bracket here. Bracket there. And maybe distribute the 2. Am I done?
No, you need to replace u with square root of
Yeah,
x.
I need to replace u with the square root of x. There it is. Does anyone have a question of why on my table of integration I use W instead of U? Anyone have a question on that? Should we check? Yeah, let's check. All right, I'm going to do a product rule right here, and then this is a subtraction, so I'm just going to do the derivative of the other one. All right, so first I take derivative of this first piece. 2 comes for the ride. Derivative of square root of x is 1 over 2 root x times e to the root x. Plus, now I take derivative of e to the root x, which is itself, times derivative of what was up top, 1 over 2 root x, times the first function, which was 2 root x. Minus, now in the second one, I don't have a product rule, so I just bring the 2 for the ride, and derivative of e to the root x is e to the root x times 1 over 2 root x. These two cancel because they're the same exact thing. And then when you just clean this one up, the 2 cancel, root cancel, root cancel, all you're left with is this, which is the original integrand. It works. That's a crazy problem, I realize that. So in the notes, what I say is this is an example where you're making a u substitution first. I should have said that, making a u sub first, not a natural one, but the one that makes most sense, which is just to try the square root of x and see what happens. Okay, I don't have enough time to do the next one, reduction formula. I'll pick that up a week from today. We have our exam. Remember, the good news is that these types of integration by parts problems will not be on the exam. The bad news is that they will be on the next exam, along with all the other techniques that we haven't done yet. So right now we have, I told you about the techniques to try and find antiderivatives. We have basic U sub, integration by parts, trig integrals, trigonometric substitution, partial fraction decomposition. We have 5 methods. We've looked at 2. How are y'all feeling?
Solid.
Great.
practice, right? Homework. Now you're going to be getting ready for the test, but as soon as that test is over, you need to get down to the homework on this. All right. It's critical. Look at how many problems I assigned out of this section. 1 through 32. All of them. All of them. Now, I will say for now, number, where is it? For now, you can skip 37 and 35. Don't worry about those right now because I have not talked about how to do those yet. That was this example right here. I didn't get a chance to do this. And that's what these two problems are for. So focus your attention on this. I need to say something else. Okay, one more thing. When you're doing your homework, if you see an integral sign and you see a number here like 2 and you see a number 3, ignore the numbers, act like they're not there, and just go find the antiderivative. Those numbers will mean something later, but for now, just ignore them, right? So just go find the antiderivative, do plus C at the end, and be done. 1 through 32 is a great set of problems. If you can get through those problems and you feel comfortable with them, you'll be in very good shape. If you finish them and you want more practice, I suggest you go to the chapter review and look at some problems there. Or come to me and I can find some more problems for you. All right, everyone, that's it. Let's wrap it up. I will post this video later on YouTube and see you on Thursday.